is mostly about security and freeing your hardware, I guess. So what most companies are trying to do is take that freedom off of us, and we try to get it back. So it's kind of a battle, and the leader in that battle is our next speaker, Ronald.
Oh, well. Now what do I do? Thank you. So I wanted to talk about an idea that crossed my mind when I was working with Jonathan on the RISC-V port. RISC-V has 4 machine modes. The OS classically, well, 3 now. The OS classically runs in, that's not me. Let's just call it ring 1. And there's a machine mode, M mode, which is higher privilege mode. Is that me or is that someone else? Oh my God. It's my phone. And in machine mode, there's no MMU, and you've got complete control of the machine. This should sound familiar. It sounds like SMM. But in the original RISC-V, there was a quote-unquote bug in that machine mode wasn't protected from being written by the OS. So your kernel could come to life and then scribble all over machine mode. And I thought that was terrific. The reason I thought it was terrific is I've suffered under things like firmware that you call into for years, and you really aren't able to optimize, say, that kind of stuff to your kernel. So when I did the Plan 9 port to the RISC-V, I thought, great, I can optimize a machine mode to Plan 9, and I don't have to work with this generic thing that was provided by some firmware vendor who doesn't know what I want to do. I can completely own the machine mode code and make it fit Plan 9 really well. And then naturally I thought, well, wait a minute, why couldn't I do that with SMM? So hence this talk. It's describing an exploration I've done of how you could do this. Another thing is that if we put SMM in Linux, and this is an example, then we don't have to count on whoever provides the firmware having done everything right. And I don't like to count on firmware providers having done everything right, even when it's us. So, how many people here have looked at the SMM relocate code in coreboot? That's great. Okay, that's really great because I'm really glad you've looked at it, but most of you haven't, and so then I don't have to skip most of my talk. So, so I'm going to quick run through SMM and then SMM in LinuxBIOS and SMM in coreboot, and why SMM will never die. Now, I've had people from x86 vendors tell me they want to kill it, and then about a year later, they'll tell me about some new feature they've implemented and they put it in SMM. So, it just, it's the same vendor. So, what can I say? I just don't think it's going to go away. And then a little bit about why persistent firmware code can actually be pretty dangerous. And I've mentioned the RISC-V inspiration, but I'll have a little more about that. And then an alternative. And, it's really good to read your slides one more time before you give a talk, because I discovered there was a slide in here that said demo. And so the good news is I just tried the demo and it works still. I'd forgotten about that. So system management mode came in with the 486. It was introduced to support power management, and here's the problem. You're running DOS1, and this is a really important thing to remember about x86. Everything in the x86 universe relates to the need to run DOS 1.0. So if you understand that explains everything. So I've got a laptop and it's running DOS 1.0 and I close the lid, and how does it sleep? Well, it doesn't, because it's DOS 1.0, it's dumb as a brick, it's just going to sit there with it powered on and run the battery to 0 and we're done. So there had to be a way to do this such that DOS 1.0 would continue to run. And if you kind of work through the principles here, you need a higher privilege level than ring 0 because DOS 1.0 is in ring 0 and you can't push it out of the way because it won't resume correctly. You need operations that are implemented in that higher level that run without ring 0 even knowing they've occurred. You need to make sure ring 0 can't mess it up. You need to make sure that certain interrupts get vectored to those hidden operations like lid close. And they've really got to be hidden in a way that ring 0 won't even know they're there, right? That's the DOS 1 promise. And you've got to make sure they can't be turned off. So now we've got to have registers we can enable and then lock down. So DOS can't even maybe mess them up or find them. And then finally, you've got to have no state leakage across that boundary. So whatever happened and whatever you did, what happened in SMM stays in SMM. So you need a design based on those requirements, and SMM is kind of one way to get there. But in the beginning, the key thing, everything in the x86, it's all about DOS 1. So that's why we still have a lot of the things we have. Well, then came evolution. If there's a place to put secret code that can never be seen and can do special things, you think vendors are going to use that special place to put that secret code? I mean, the question answers itself instantly, right? Of course they are. So, and then further, if the secret code is written to lowest common denominator coding standards by people who actually don't write software for a living, and then they hand out to every vendor, and said vendors don't write software for a living, and those vendors put in random features designed for customer lock-in, you think it'll be full of 0 days and nasty bugs? Okay, we've answered that question too. I don't even know why I asked it. So here are 2 questions that answer themselves, and that's how we end up where we are today. SMM is a horrible, horrible problem for security, and we want it dead. So we either want it dead or we want to control it. I really have been impressed by the number of SMM bugs I found once I started looking, and they all kind of get back to pretty poor coding standards and just lack of knowledge. Not in a coreboot case. Coreboot SMM code is perfect. So anyway, there's another thing though, people keep saying, I want to kill SMM, I want it gone, removed from the instruction set, and even x86 vendors say that to me, and then in the next breath they say, but, well, 3D X-Point, we've done some really cool stuff and we buried a lot of it in SMM, so we really want SMM back. And the fact is, no feature ever leaves the x86. Why is that? Because of DOS 1.0. Andrew Waterman likes to point out that the DAA instruction, which is decimal adjust and add, I think, no one has ever used that in the history of the planet. It eats up 1, 2, 3, 6 of the instruction code space of the x86, it'll never go away, right? Because maybe there's some program that runs under DOS 1 that used it once. So, you can think, well, in some ways it's real easy to deal with SMM. Don't enable it, lock the memory, just lock it completely out. But in other ways, it's really hard because there might just someday be a thing that really needs it. And, the thing that bothers me a little about this is this idea of SMM tends to start infecting other registers. So I mentioned that the RISC-V kind of had this machine mode that you could control and rewrite from the operating system. That's no longer true. The latest privilege spec for RISC-V has an SMM-like thing. Are the vendors going to use it? Yeah, of course they are. So it kind of is impossible to kill. I've kind of tried to talk to about this in the RISC-V community, but I haven't really gotten very far. So that's SMM. That's how we are where we are. So let's do a quick overview of SMM, and then I'll talk about the prototype. Now, little digression. No, you don't need SMM. We had a meeting in Los Alamos with an Intel rep in 04, and the guy stated very confidently that you can't build a working server without an SMM handler. And we kind of said, well, Linux Networks 100,000 plus systems don't seem to agree with you, and they're all running LinuxBIOS, and SMM is turned off. So the only thing I ever saw SMM do in my high-performance computing universe was make life miserable for applications programmers. And it's a simple reason. If I've got 4,000 cores running an application and they're running very tightly in synchrony, as they tend to do in HPC, and one of those cores gets in 20 milliseconds late because of some stupid SMM thing that nobody cares about, you've just cost me about $1 million per year because you've made my entire machine a little slower. So we didn't even put SMM into LinuxBIOS in 2006 or so, 7 years after the project began, but there was this random i945-based laptop that needed it, and so you did it. Stefan's fault, I had nothing to do with it, so just so you want to know, you can yell at him. So anyway, a little bit of basics on SMM, although a bunch of you already know this. At Power on Reset, the hardware sets this magic register that they added called the SM base to X30,000 on all the cores. So that's startup. Back in the day, all the cores meant 1. So it kind of makes sense, I guess, that it did it on all the cores. And then on the system management interrupt, it actually saves the state, and it, like everything else in the x86, SN base points to a 64K size region, right? And that's just the way we do things on the x86. So on an SM interrupt, state is stated at SN base plus 0xF something something. Now here's an interesting question. On an SMI, state is state. How much state? For a long time, we didn't know. So if you look at the coreboot code around this, we kind of just say, make it hex 400 bytes, and we'll never regret making it hex 400 bytes. So that was a smart decision. Was that your decision? Or was that Patrick? We don't know anymore. Okay, that was a really good move, because later on, somebody actually started saying, yeah, it's hex 400 bytes. We might have said it was smaller, but we were wrong. And so that actual offset used to be a little magic, but it's now kind of standard. And if you look at coreboot now, you'll see it's OXFCOO. And this is kind of weird, but there's this stub that starts at hex 8000 offset from SN base, and then typically that'll jump down to SN base. And the idea here is you have your unique state that is saved there, and then you start a stub, and the stub kind of takes care of like figuring out which core you're on and what to do, and then it jumps down to the 0 offset. So the stub is per core. There's sort of a generic handler at 30,000 in the initial thing. And the question is, well, wait a minute. I just said that I store state at SCOO from SN base, and I jump to various places. So how do I differentiate where different cores state different things? Well, you manipulate SN base. And I'll get to that in a minute, but messing around with SN base is kind of the core idea, one of the core ideas of SMM. And again, this SN base is kind of like another segment register, like CSDS, CS, and all that, but it's kind of off in the IO space, and there's kind of an assumed 64K limit, except it's not really 64K on just about anything anymore. So how do you manipulate, it's not me this time, how do you manipulate SN base? Well, SN base is kind of like an MSR, and it's very, very odd, at least to me. You are in SMM, and if you look at memory at 0xFEFC, typically on Intel, it looks like memory, but it's a register. It's a per core register, and if you change it, the next time you take an SM interrupt, it'll use that kind of thing that you just said. It's something that looks like memory, but it's really a register to figure out where to go. So if you look at source, coreboot, whatever, SMM relocate base, there's a really kind of very nice explanation of how all this puts together. And one of the tricks here is this particular version of how this is set up has got to be serialized. Again, because everybody starts at hex 30,000. You can't have everybody jump in at once with an SMM because they'll all save at the same place, so that's not going to happen. So we do that one at a time. And there's some neat stuff that came in afterward. Is that me, or is... We still don't know what that is, but I've got my volume turned off. Sorry, guys. I have to tell someone to stop chatting. I can't exit Kernel because it's running this presentation. Anyway, so you kind of have to do this one at a time. Every core is going to maybe change SN base, and they're going to change it to a different value. So they've got to do it one at a time, or else they'll all save their state to the same area, and things will get pretty damn confused when they go to return. So the first rule of SMM Club is you never talk about SMM Club. You can do things in SMM that you can't do outside SMM. So when you're in SMM and you touch that weirdo memory location and offset something from SN base, that'll work. When you're not in SMM and you look at that, it just looks like any other piece of memory. It's a very, very strange mode. It goes back to the 46 days before we knew about things like MSRs, and it's not surprising, it's just kind of weird. So if you look at the coreboot SMM relocate base, it's kind of interesting. It sort of sets things up, and then it puts a piece of wood right here, and then it walks into the piece of wood and trips, and it falls into SMM. Okay, and then it does some stuff in SMM, and then it does an RSM instruction and jumps back out. And magic stuff has happened in SMM Club, and now we're good to go. So that's kind of, the model of SMM is you're continually tripping over your own toes. I find the whole thing pretty strange. It's kind of very early 1990s microprocessor design. before we knew a lot of things. So I still argue, though, reading the SMM relocate code and the handler, I was pretty confused when I started looking at it. I actually found it very interesting and worth reading and understanding. The comments are good, so give it a go. So anyway, I'm not very good with graphics, but I've got this wonderful picture, and you're just going to have to live with it. So we have this common handler at A4 zeros, right? This is where all the code is in memory at A4 zeros, and we do this little trick. So here's the core 0 stub and stack. It's at this plus 8,000, and so that's good, right? What do we do for core 1? Well, I'm sorry, there's the core 0 save. I told you I wasn't good at this. So here's the core 0 stub and stack, and there's the save state. So how do we make things go to the right place? This is the fun part. Core 0's SM base is A4 zeros. Core 1's SM base is BFCOO. All right? So now when I add my 8,000 to that, I come here, and when for the save state, I add BFCOO to that, I come to F8 2 zeros, right? Core 2's is further, the SM base is BF800, right? And so when I offset from that with those two constants, I end up there and there. So that's kind of the trick. And that's what SMM relocate does in part. It kind of sets this SM base with this changed value in each one. And then the handler in each of these things does actually a jump to segment A offset 0. So it normalizes it. So roughly, you determine SM base MMIO location, and you just figure these things out. Then you do some stuff, and you clear this SM status bit and PM1 status. And EOS is your way of saying, it all worked out, and I'm exiting the SMM thing, and things are good. And if I get another SMM event, please come back. And if you don't set EOS, you'll never get another SMM event. So you really want to remember to do that. And that's kind of it. Now, back in the RAM stage, when we're all done this ring 0 code locks down the SM RAM and some other control bits. So that's kind of the thing that turns on SMM, and the memory that is the SMM handler disappears, and you can't turn it off, and you can't look at it, and you can't even really completely tell what might cause you to get into an SMM type situation. So now there's an SMM handler. It's an SMMhandler.s. The actual implementation isn't completely consistent with the comments in SMM relocate.s, partly because I think it's evolved and there was no need to change SMM relocate. So you want to read both, but you just have to keep in mind that they're not completely entirely consistent with each other. The stub in SMM handler is really quite nice, okay? So for every single core, it basically kind of gets the stack right, and does a far jump, and it's done. So that is also worth looking at just to see how it works. And then all the rest of it's common code, and it uses the local APIC ID to figure out, which core you are. And I thought this was quite cute. One of the SMM exploits was this crazy thing where you kind of overlap the local APIC address and the APIC code, and I forget more about it, but Patrick fixed it in 2015, not long after it was reported. And I don't know who else fixed it, but probably not many other people. So there was a crazy, crazy SMM exploit that was pretty cool, and I went and looked and did a git blame, and there's Patrick already repaired it. So, and in coreboot, we're in 8086 mode shortly, and then we jump to protected mode, and we do everything in 32-bit handler in SMM. All right, so here's some questions. That was a very, very quick view, I know. Because there's not a lot of time to get too deep into this. Is SMI a higher priority than any ring 0 interrupt, including NMI? This is a question I actually have for all of you. That seems to be that way to me. Is that correct, would you say? If I'm in an NMI handler and I take an SMI, I'm going to take the SMI. Good. So are there any ring 0 activities that could ever be blocked? Because it could ever block an SMI? I can't imagine that there would be. I think an SMI is always going to take precedence over anything else you might be doing, right? Okay, that's interesting. So here's one question I've really been wondering about. Do you think we could run all the SMM code on the BSP and call it a day? Is there any reason to ever run it on an AP? Isn't the SMM code all serialized anyway?
Sometimes you want to run it on silence.
Okay. Okay, so that's a shame, but oh well. The origin of the all cores helped for SMM, right? Because pretty much when you take an SMM, I don't know how many people know this, if you've got a 256 core machine, and you take an SMM, the design is that everybody stops while one of the cores handles it. What is the origin of that? Is that just bad programming?
There's actually a software mechanism.
Yeah.
The documents is referred to as string coordinate.
Yes.
Of how to basically send a certain load of SMIs to a certain core.
But why do all the cores have to wait until one core has done the SM?
Well, he did it because Linux kernel was crashing a little bit.
Okay, that's good to know.
I'm not sure.
Well, it's something I'd like to look at, because right now the way SMM is said is supposed to be working is you get one SMM interrupt on one core. I gotta love a Mac. And everybody waits while it's handled by one core. And this is actually, I know, been an issue on some of the many core systems because everybody stops while one core handles this SMM interrupt. And I just don't think it makes sense. So the big question is what blocks us from treating an SMI as a super high priority interrupt on the BSP? So you've already explained a few things. But that's one of the things I'd like to try and figure out, right? So. Linux implementation questions. Do I disable the SMM setup in coreboot? And for the moment, I let coreboot do the SMM setup, but I leave it in a mode that the SMM can be overwritten and changed by Linux. SMP issue, I hope we can talk more about this over the weekend. I've still got questions. Should I run a special SMM handler in Linux that's sort of like an SMM handler, but it came from the kernel, not from coreboot? And in the example today, I actually used the Linux kernel 64-bit trampoline to run in kernel an SMM handler, rather than sort of the usual model of this thing that's often a special place doing special things. And that actually means if you use the 64-bit trampoline, you're using the kernel page tables. So you actually really are literally a standard interrupt handler in the Linux kernel when you do this. How to structure the code, I'll probably get shot for this. I pulled chipset code into Linux kernel from coreboot. I don't know. The SMM chipset stuff seems to be becoming more and more generic. It used to be like very special for each chipset, but there seems to be comments in the code that there's sort of a generic model for SMM enablement now. So I'm not sure it's such a bad thing. All right, so here are the pieces. If you look at ArcEdit x86, you'll see there's a directory called real mode, and real mode is kind of I'll only talk about x86-64. Real mode is the x86-64 architectural stuff for handling things related to real mode, and under that is a directory called RM, and that's the stuff that actually, it's the trampolines that run in 16-bit mode. So in RM is the code that handles trampolining back and forth between 16 and 64-bit. And the stuff I added in RM is the chipset stuff I mentioned, the SMM handler and the SMM relocate code, a file I called for old time's sake, LinuxBIOS.c, and then the chipset stuff. So if you look, I've added 6 files and I've changed a few more than that, but the changes aren't huge. So kconfig kbuild, a new config variable for LinuxBIOS, just got to do it, right? And added it. The way you hook into real mode stuff is a little baroque. Basically, you kind of build a giant blob from all those .s files in RM, and then you kind of get symbols out, and then they align with a struct. So you kind of added a struct, and the way the 64-bit code in Linux locates code is it looks in this struct. It's pretty insane, but it works really well, and it was a piece of cake to set up. So in real mode, you set up these stubs and trampolines. So that was that piece. And then when you hook it all together, it actually is pretty darn easy, right? You just change the real mode RM setup a bit, And you set up some code in real mode slash, because that's part of the kernel as it's running in 64-bit mode, and you're kind of done. So I actually, by accident, lost the whole piece, and I had to reassemble it at some point, and it actually was better the second time I did it. So, you know, rm slash, you add a few things to the make file, and you're done with that. Little note on LinuxBIOS real mode, you write these .s files with symbols that are kind of named PA, whatever, and that's because there's a Perl script or something that strips this stuff out. And they have this crazy NM pipe to set pipeline that automatically makes PA-sims.h, and that gets included in something else. It's kind of the typical Linux sideshow of building things involving NM and set and CPP and all kinds of games. There's even a CPP pass on a low script, but when you're done, you have the real mode piggyback, and that kind of gets linked in. Yeah, to use the blobs, I actually grabbed the coreboot SMM, and that works fine. I think the biggest thing I had to change is we have the first argument to print K, which is your priority or whatever, and I took that out. Code's mostly the same. You can't just reference address A 4 zeros in the kernel, of course, because that's not a kernel address, so you gotta, VMAP it in, big deal. This isn't really SMP ready yet, that's just due to me running out of time, actually. And then I just changed the handler. So this isn't really kind of working in Nerf yet, but it might. And you can't do kernel address space layout randomization. That doesn't quite work yet either. The handler is really different. The handler just says, here I am. So the handler is just a function in the kernel that gets called as part of SM interrupt handling. And one of the things I found is kind of funny, I don't quite know why this isn't fixed, or I might just have to try and push a change. The Linux 64-bit trampoline that goes from 16 to 64-bit mode doesn't work if you've got non-executable paging support, because the NX bit is the higher bit, and it just goes to pieces when NX is enabled. So you have to do it with no NXE. So there's my very complicated SMM handler in the kernel, which is not very exciting. And now I'll do the demo that I didn't actually realize until this morning I said I'd do. Let me find the window. Yeah. So for anyone who cares, this is no. This is actually using uroot, and I have a piece of Acros in here that is called the monitor that interacts from the kernel. So raise the SMI, and we're as done, and now it's done. So we've installed an SMI handler that vectors to the Linux kernel, and a lot of times in the early development, I knew I hadn't done it right because the kernel would explode and die. So now let's just do. So that's it. I just ran an SMM handler that's part of Linux. So that's the whole thing. This isn't a Q35 QEMU. I haven't done it on real hardware yet. I don't really see any fundamental reason it wouldn't work on real hardware, but I just haven't done it. So, why would you ever do this? All the platforms people I know want SMM gone. They want it out of their life. They hate it. They hate the 16-bit trampoline. They see it as nothing but a vulnerability. I'm fine with that. I really like the idea of killing SMM, but if we can't kill, we have to think of something. And status quo is not really acceptable. So, and further, SMM seems to be appearing on other architectures. Not a good situation. SMP, yeah, SMP. Let's move right along. SMP isn't working yet. What's the programming model? Do we think of this as a nested SMI, a higher priority SMI? How do we think about SMM when we're jamming into the kernel? And what about the things that SMM does, like sleep? What's the right way to deal with that? On a server platform, you don't, because you don't really do that kind of thing. But I'm not really talking about laptops here, so that's a different problem. Here's the where. I'll just leave that up. I just quick pasted that. you're welcome to take a look and tell me what I got wrong. You'll see the changes aren't that extensive. It ended up being really simple. It's more, it's not the code that's the issue here, it's more the philosophy, right? Let's provide the right way to handle SMM, assuming we can't kill it. And I know on RISC-V, my feeling is I'd like them to leave machine mode open so the kernel can put the proper machine mode in. I don't know if that'll happen. And on x86, I'd like to see if we can make this work. So that's it. I can put this back on schedule. Any questions? Well, that was easy, no questions. All right. Oh, yeah.
There's one question. What is NERF?
NERF. That's the other project. NERF stands for, so UEFI stands for Unified Extensible Firmware Interface. NERF stands for Non-Extensible Reduced Firmware. And basically, we had the discussion of UEFI this morning, and there was a great diagram that showed the SEC and the PEI, and then UEFI itself. And NERF replaces all of the UEFI with Linux kernel. So it's actually another way of saying LinuxBIOS. And I can talk about that over the weekend. It's not really for this part of the conference. All right, thanks everyone.
So next up we have a small coffee break that has been extended by 15 minutes. So we see each other and begin back again at